We live in an expanding universe, represented here by an expanding cube that shows how one small region of the entire universe grows with time. You have already learned how Hubble's constant tells us the current expansion rate, but how has that rate changed with time? Astronomers long assumed that gravity should have caused the rate to slow with time, but evidence now shows that the rate is accelerating. In this video, we will briefly investigate this evidence. To simplify our diagrams, we will focus only on a circular slice through the cube, so that the expanding universe is represented by the growing size of this circle. This diagram shows four possible models for how the expansion rate may have changed through time. The present represents the universe as it is today, which all four models must agree on, since we know the current size and expansion rate of the universe. Down represents the universe in the past, and up represents the universe in the future. Let's start with the recollapsing model. In this model, gravity will eventually halt the expansion, so while the expansion continues for a while into the future, it eventually stops. At that point, the universe contracts until its fiery end. The strong gravity in this model means that the expansion must already have slowed significantly since the Big Bang, which is why it shows the expansion rate to have been faster in the past. Next, consider the critical model, which gets its name because it assumes that the average density of mass in the universe is exactly the critical density, and that the gravity of this mass is the only thing that affects the expansion rate. In this model, the expansion gradually slows, but never quite stops. The third, or coasting model, assumes that the expansion rate has never changed, as would be the case if gravity were extremely weak and nothing else affected the rate. That is why it shows the universe expanding at a constant rate through time. The fourth model also assumes that gravity is too weak to stop the expansion, but adds a repulsive force, which we usually call dark energy, that causes the expansion to accelerate. The expansion therefore starts relatively slowly, but gets faster with time. Now consider this question. Which model predicts the fastest rate for the expansion of the universe in the past? Is it the recollapsing model, the critical model, the coasting model, or the accelerating model? The answer is A, the recollapsing model. This model has the shortest time from the Big Bang to the present universe, which means it must have had the fastest past expansion rate. This fact explains why each model predicts the Big Bang at a different time in the past. A slower past expansion rate would mean that the universe would have taken longer to reach its present size, so the predicted time of the Big Bang is further in the past for each subsequent model. The key question is which of these models best matches the actual universe. To answer this question, we need to be more quantitative about the model predictions, which we do by showing the four models on a graph. The vertical axis represents the relative size of the universe, or average distance between galaxies, starting from the Big Bang and showing larger sizes going upward. The horizontal axis shows time. 0 represents now, with the past to the left and the future to the right. As an example of how to read the graph, notice that for time 0, or now, all four models agree on the present size of the universe, as they must. You can now see how the graph shows the models we have discussed. For example, the recollapsing model shows the universe expanding rapidly at first, but later collapsing, while the coasting model is a straight line because its expansion rate is always the same. To determine which model best matches the actual universe, astronomers must measure the expansion rate at different times in the past. In principle, this simply requires comparing the expansion rate at great distances, where we see far into the past, to the expansion rate nearer by. In practice, it is difficult work, because it requires precise distance measurements for very distant objects. Recall that our best method for such measurements relies on the use of white dwarf supernovae as standard candles. Despite the difficulty, over the past couple decades, astronomers have collected the data now shown. Notice that these data fit the accelerating model better than any of the other models, providing strong evidence that we actually live in an accelerating universe.